Hi everyone and welcome back. Today we will solve the lead code problem walking robot simulation. A robot on the XY plane that starts at point 0 and 0 facing north. The robot receives an array of integers which represent a sequence of moves that it needs to execute. The three possible types of instruction that the robot can receive is -2 means turning to the left 90 degrees, and -1 means turning to the right 90 degrees, and a number from 1 to 9 that means moving forward k units, 1 unit at a time. Also, there are some of the grid square that are obstacles. If the robot runs into an obstacle, it will stay in its current location and move on to the next code. Our goal is to return the maximum squared distance that the robot reaches at any point in its path. And keep in mind that moving to the north means that increasing the y direction, moving to the east means increasing the x direction, and moving south means decreasing the y direction, and moving west means decreasing the x direction. So, in this problem, we are given a list of commands and obstacle position. The robot starts at position 0, 0 and facing north. So it's moving or facing to the up direction. The commands can be moving forward or turning right or turning left. Our goal is to return the maximum square distance from the origin. The key idea here is simple. We need to simulate the robot movement step by step. But there is a catch. We must quickly check if the next position is an obstacle or not. To scan for obstacles, we have three different ways. The first one, as the robot is moving, so let's say at position X and Y, for each position X and Y, we will scan the obstacle vector, checking if that position is an obstacle or not. But this solution is too slow. The second one is to store the obstacle, each position that represents an obstacle, in a set. And then at each movement of the robot, we check if this position is located in the set or not. Although this solution will work, it gives us look-in, lookup. The third solution, and the best one, is to use a hash set for constant time check. And to do so, we need to encode its position of the obstacle into a single number. How to do that? We need to encode each position in the obstacle at a single number. To do that, we will use this formula. So imagine we will store each position as a unique value using this formula, which is, let's say, long key equal long of x shifted to the left 32 bits, and this calculation is ordered with unsigned and of y. If you still didn't get it, let's explain it step by step. The first port, long x shifted 32-bit to the left. Here we move the x value to the high 32-bit of the number. Imagine that our key looks like, or we are dividing our key into two parts. Our key is represented by 64-bit. So we have here, let's name it the high 32-bit, and here we have the low 32-bit. So when we move our x value 32-bit to the right, that means that our x is located in the high half, and this half still 0. And for the second board, unsigned int y, that means that we keep the y in the lower 32-bit. So similar to this one, here we will have 0 and our y value will be located in the lower half. So when we ORing these two parts together, at the end we will have our x in the higher half and our y in the lower half. So finally, both values are packed into one 64-bit number. X and y now are stored in separate half, no overlap and no collision, and every x and y position in the obstacle is now mapped to a unique key. So let's move to the code. Here we will define two variables, x and y, and both initialized to 0. This will track the current position of the robot, and also we will define a variable, let's call it farthest, which should hold the final result. After that, we need to encode each x and y position in obstacle into one number. So for O2, let's name O in obstacles. We will use our formula here to calculate the key. So our key will have our x will equal our x shifted to the left 32-bit, ORed with our y. And semicolon. After that, we will store that key. So we have to first define a hash set. Let's name obstacle set, and we will store that unique key in our set. So here we encode our x, and let's name it x and y of x and y into one unique number. After that, we need to represent our direction We can move in four directions: north, east, south, west. So we need to represent this direction as four vectors. So here I'll define direction vector of vector integers. Let's name it dia, and I'll define it as four vectors. The first one is moving north, so we are incrementing the y direction. The second one is moving to the right, so we are incrementing the x direction. The third one is moving south, so we are decrementing the y direction. And the last one is moving to the left, so we are decrementing the x direction. And to move between the different directions, we will define a direction index variable that is initially 0, which means that it points to the first one, which is north. So we are using our dir index to track where the robot is facing. So moving right will increment the dir direction, and turning left will decrement the dir direction. So let's implement this logic. So we will scan the commands. So for int command in our commands vector, we need to check if our command equal -1, then we need to increment our dir index by 1. So our dir index equal dir index plus 1. But you have to take care of something. As we incrementing the dir index, we will exceed our dir index range. So to keep this index in range, we need to make it modular 4. So when the dir index reach the value of 4, so we are beyond the range of this vector. So modulo 4 will return us to the range again. Else our command is -2, which means turning left, and this also will decrement our dir index by 1. But again, we don't need to be outside the range from the left side. So to make it right, we need to add 4 here and also use the modulo 4. And to make it a bit faster, we don't need to recalculate this addition each time. So let's make it +3. And the last thing is the moving forward logic. For each forward command, we move one step at a time. And we need, before moving, we need to check if the next position is an obstacle or not. And if yes, we stop immediately. Otherwise, we continue moving. So here we need to move key steps. So for end k equal, let's name it I, for int I equal 0 and I is less than command and plus plus I, we need to calculate the new value. So let's name it nx, which equal the current x value plus the direction value, and the same for y. We have a new y value equals the old y value plus the direction. And also we need to repeat the calculation of the unique key. So let's say, let's copy this again here. But this time, instead of using x, we'll use the new x and the new y. After that, we need to check if this key exists in our set or not. So and if the key exists, we break immediately. Otherwise, we set x to equal the new x and y to equal the new y. And also, we don't need to forget that after each command, we need to compute the distance from the origin, which is x squared plus y squared, and we need to keep track of the maximum. So here we need to store in our furthest variable this calculation. So our first variable will equal the maximum of the current value plus x multiplied by x plus y multiplied by y. And at the end, we need to return the furthest value. And this is the overall solution for this problem. Let's run it. Oh yeah, so we have an extra process here, most probably here as well. So let's run again. Well, it seems something went wrong here. Yeah, terrible mistake. I'm using the formula from the comment instead of adding the right variable. So we'll use our variable of 0 and of 1. Let's run again. And here we go. All test case passes. Let's submit it. So as you can see, in terms of complexity, the complexity here is O of n plus m, where n is the commands and m is the obstacles. And thanks for hashing, each lookup is constant now. And that's how you simulate the robot efficiently. And this is all for today's solution. If you like it, please like and subscribe to the channel for more videos like this. And thanks for watching. Bye.